Welcome to This Explainer. Today, we're exploring a hyper-engineered, incredibly high-stakes world that most of us only ever see flashing by on the highway: medical transport. We are going to unpack the exact science, the strict regulations, and the intense manufacturing logic that separates different types of ambulances. Okay, let's dive into this. Right out of the gate, we need to instantly shatter a pretty common myth. Modern ambulances, they are not just passenger vans with a coat of white paint, a stretcher, and a siren bolted to the roof. Absolutely not. These vehicles are meticulously engineered clinical environments on wheels. Literally every single inch of space is optimized for human survival. So here is our roadmap for This Explainer. We're covering 5 key areas. 1. The hospital on wheels. 2. Two different medical missions. 3. Engineering the technical gap. 4. Medical-grade manufacturing. And 5. Global procurement strategy. Let's get right to it. Section 1. The hospital on wheels, defining the boundaries. You see, the intensity of an ambulance's structural conversion isn't just random. It is dictated by strict international benchmarks like the EN 1789 standard. Under this, we basically get 2 main categories. First, we have emergency ambulances, specifically Type B and Type C. These are essentially mobile ICUs engineered for high-intensity field rescues. They are the absolute last line of defense for life, the highly equipped responders you desperately want during a critical emergency. On the flip side, we have non-emergency ambulances, which are used for patient transport services, or PTS. If emergency units are the defense line, well, these PTS units are the lubricant of medical logistics. They handle routine inter-hospital transfers safely and efficiently. Section 2. 2 different medical missions. Engineering the technical gap. So the crucial point is how these different medical missions translate into vastly different engineering requirements under the hood. An emergency unit is hyper-focused on the golden hour, that critical fleeting window where literally every single second counts for a patient's survival. That intense focus requires massive medical gas redundancy and extreme functional integration. In stark contrast, non-emergency units shift their engineering goals entirely towards space efficiency, passenger comfort, and maintaining a lower operational overhead for all those routine daily transfers. Now, what's really interesting about this slide is the sheer scale of the technical gap between the two. It's staggering. Take the electrical systems, for example. An emergency unit requires a 2,000-watt pure sine wave inverter. Basically, it's a system that delivers perfectly clean, uninterrupted power, so highly sensitive, life-saving machines never glitch. To put that into perspective, it's like powering a small, highly specialized house while barreling down the road. A non-emergency unit, it only needs about half that power. And notice the oxygen supply payloads too. Emergency units demand dual route controls with heavy 10-liter cylinders, which makes these mobile ICUs incredibly heavy. Because of these massive payloads, picking a chassis isn't about brand loyalty at all. It's an exercise in life-saving spatial logic. The Ford Transit series is basically the gold standard for emergencies because its high roof actually allows medics to physically stand upright while performing CPR. That's a huge deal. Meanwhile, the Toyota Hiace is agile enough to weave through dense urban traffic for routine transfers. And of course, specialized 4WD platforms are strictly necessary for rescuing patients in off-grid mining sites or out on rugged, unpaved terrains. Section 4. Medical-grade manufacturing. Craftsmanship meets safety. When we look at professional emergency units, they utilize what's called seamless integration technology. We're talking vacuum-formed or mold-integrated interiors. And actually, this isn't just to make the back of the ambulance look sleek and futuristic. By eliminating seams and sharp corners, you completely eliminate the microscopic hiding spots where bacteria love to thrive. Imagine trying to deep clean your own kitchen in about 5 minutes flat, using harsh, highly corrosive chemicals like concentrated hydrogen peroxide. Well, that is exactly what these interiors are engineered to survive, day in and day out. And hey, it's not just microscopic threats, it's massive physical forces. Think about the intense physics of a high-speed emergency response, sharp cornering, sudden, really aggressive braking. Because of this, professional manufacturers heavily reinforce medical cabinets and stretcher bases. Every single heavy equipment mount has to pass incredibly strict pull strength and impact tests. Why? Because the absolute last thing you want during a collision is for heavy defibrillator or a full oxygen tank to rip right off the wall and become a deadly projectile inside the cabin. Section 5. Global procurement strategy. The OEM evaluation logic. So, with all this complexity, how do hospital administrators and government agencies actually navigate this life-saving procurement puzzle? Well, procurement managers typically evaluate their global fleet needs based on three strategic pillars to find the right OEM, or original equipment manufacturer partner. First up, the application scenario. Are they running a high-spec urban emergency system, or are they seeking maximum commercial ROI with routine transport? Second, regulatory compliance. They have to pass strict destination standards like EN 1789 or CE marks. And third, customization capability. Finding a partner who can provide modular layouts right down to the exact type of oxygen outlets used in their specific region. This rigid, high-stakes checklist is exactly why global buyers frequently turn to mature manufacturing hubs like China. The big advantage here is striking a perfect balancing act, maintaining those strict clinical necessities while still meeting commercial realities. These specialized factories offer highly flexible customization across different chassis, delivering cost-effective production without ever sacrificing those critical safety standards we just talked about. Plus, they provide heavy export-oriented support for complex regional documentation and compliance. Now, as we look at customization, a very specific and frequent question tends to pop up in modern procurement. What exactly is a negative pressure ambulance? And this brilliantly illustrates how modern engineering rapidly adapts to unseen crises. A negative pressure ambulance uses high-efficiency particulate air, or HEPA filtration, to maintain the patient cabin at a slightly lower pressure than the outside atmosphere. This precise invisible barrier of air control prevents dangerous pathogens from escaping the vehicle. It's an innovation that became absolutely vital for safely transporting highly infectious patients during global outbreaks like COVID-19. Here's another major operational question buyers ask. Can a standard non-emergency unit be repurposed for an emergency mission during a sudden crisis? Well, while it's technically possible in an absolute worst-case scenario, it is highly, highly discouraged. Remember that massive technical gap we looked at earlier? Standard units simply lack the high-power inverters and structural mounts needed to reliably run a life-saving ventilator under load. The infrastructure just isn't there, and you simply cannot cut corners on power when a life is on the line. So, how long does it actually take to build these customized marvels of engineering? Just 25 to 60 days. Standard transport units can usually be manufactured in about a month. But if you're commissioning a high-spec ICU unit with complex integrations, like those negative pressure systems or satellite communication links, the lead time stretches closer to 60 days. Think about that. You are essentially building a bespoke, crash-proof, fully functional hospital room from scratch in just 2 months. Let's move to and see how this builds into the bigger picture. Ultimately, choosing between these units or picking a specialized manufacturing partner isn't just a basic price check. It is really about matching medical efficiency with resource allocation. It's a long-term strategy that impacts both the financial health of a medical system and, far more importantly, the physical health of the patients it serves. We've seen exactly how standard vans are completely transformed into highly specialized rolling ICUs through rigorous engineering and smart global supply chain strategies. But as global health demands continue to evolve at absolutely breakneck speeds, how will the next generation of hospitals on wheels adapt to the unseen crises of tomorrow? It is a fascinating space to watch for sure. Thank you so much for joining me on this explainer.